Hi there. I had a few requests to look at the Fourier series at the end, so I've put it into a video so I can concentrate on the other aspects of the course in the lectures. So Fourier series is a really important aspect of physics and engineering. We use it quite a bit in electronics, in quantum mechanics and solid state physics. And let's have a look at some slides. But before I do that, I want to go back and reiterate what we've looked at over the past week. So we talked about how we could draw a circle and define that circle with some vector, call it r, the radius vector, and that radius vector tracked our path around the circle, and that radius vector doesn't change magnitude, but it changes direction. And that direction was defined by our parameter. We called it u, but it's an angle, so we can call it whatever we like. So that angle defined the path direction that we took around that circle. And then we went one step further and said, okay, instead of having a constant r, we could have a path that was just random, and it defined our radius vector r, but that r now changes in magnitude and direction as we transverse this path. So at some future point, our r over here is smaller than it was before. And so we can use these vectors to show our function that we have, and use those vectors to get interesting physics out of the function. Okay, so going along with that idea, remember our radius vector has ijk components, and in this case I've called it v, so it might be a velocity vector. And so our velocity vector has an I and a j and a k component, because we've determined that there's a xyz coordinate system that we're dealing with. Now, it doesn't have to be an xyz coordinate system. It could be an angular coordinate system that has theta, phi, and a radius vector involved in it. But in this case, we're looking at xyz to make it easier for us. And these unit vectors, I, j, k, are called the basis vectors of the coordinate system that we've chosen. And they define the components that the vector has. So the components vi, vj, and vk are how much that vector has in each of the basis vector direction. Okay, so that makes up our vector quantity. So having this idea of a basis and coefficients can make it a lot easier to do some physics that we want to do. And it'd be really nice if we can write some complicated function, fx, as just some sum of basis vectors that we have. And those basis functions need to be easier to work with than the original function. Okay, so in your mathematics that hopefully you've done in first semester, you should have been taught about Taylor series expansion. So if we have some function and we want to approximate that function at some point, So let's say I have some function, I'll just do a sine, and we pick a point on that curve, I call it point D, or point A, and we want to approximate that. We can do a Taylor series expansion, and we have multiple parts of that expansion to approximate the function around that point. Now, the Taylor series expansion utilizes polynomials, and polynomials like this can if you have enough of them, you can represent anything you like. You can even fit the outline of an elephant as long as you've got enough polynomials in the series. So they can be quite powerful for what you want to do with them. And if you haven't seen Taylor series before, I suggest you go to the Khan Academy and look up Taylor polynomials. There's a great online tutorial on Taylor polynomials. Okay, so in our Taylor expansion, we've now got our polynomial x minus a to the power of n, and n goes to infinity, so we can have an infinite number of polynomials, and each polynomial is the basis that we've chosen. The coefficient Cn is written down the bottom here, and it's actually the derivative of our function. So C1 would be the first derivative, divided by n1 factorial. C2 would be the second derivative, divided by 1 factorial. And that's evaluated at the point x equal a or x equal d, as we have over here on the side. So that's a Taylor series expansion, and basically we've got coefficients and we've got a basis, in this case a polynomial basis. But in physics, it's really interesting if we use trigonometric functions like cosines and sines as our basis functions. And why is that? Well, in electronics we use signals that are sines and cosines. In quantum mechanics and solid state physics, we talk about how photons of light, if I draw a little photon and it zooms across and interacts with some matter or surface, these photons are EM radiation, so they're waves and have single frequencies. And they're easily represented by a sine or a cosine function. And not only is the photon of light, or the EM radiation, wave-like, but the solid is also wave-like. So we can get reasonable solutions to a lot of physical problems that we see in physics. Okay, so the simplest case is when we have a periodic function. And so that has a periodicity, in this case, in the x direction. So if we plot our sine function, for example, that looks like this, then it keeps going off into infinity, but it's really repeating the same thing over and over and over again. So the distance in x, that repeating unit, is the wavelength lambda. So we've got our function now as a periodic function, and we can represent that as our Taylor series expansion as a function of cosines and sines. So here's our Fourier series, and we have coefficients a n and b n, And we also have our basis, are our sines and cosines. And remember, our basis vectors like I, j, k had to be orthogonal, and indeed it may not look like it, but these basis vectors are orthogonal, and you can go through the mathematics to prove that. So here's our Fourier series in our x. So we would have x there, and that's f of x. We can also do the same thing for something that's oscillating in time, same as we saw in first semester with waves, and you'd have the same sort of thing. It's something oscillating in time. Instead of f of x, we would have f of t. And our cosines and sines, instead of being nkx, would be n omega t. So this one would be n omega t, where omega is the frequency. Okay, so we have the basis of our Fourier series. The coefficients are actually integrals of our function. So we have a naught is our first of our series, and we also have an and bn as components to the series. Now the powerful thing about doing the mathematics like this is because we only need to look at it over one period, because it's repeating over and over and over again, we only have to do the integration over one wavelength. So it saves a lot of computation time.